Hello, welcome to our PODC 2020 talk. Sleeping is efficient, MIS in constant rounds, node averaged awake complexity. I'm Gopal Pandurangan of University of Houston. This is joint work with Soumyottam Chatterjee of Georgetown University and Robert Gmyr of Microsoft. So MIS is, of course, one of the fundamental problems in distributed computing. It has been extensively studied for the last 4 decades. And it started with about 35 years ago by the celebrated results of Alon Baba Itai and Luby, who presented randomized distributed algorithms for MIS that ran in order log-n rounds with high probability on n-node networks. So what is, after these 4 decades, what are the best known algorithms that we have? It is still, for general graphs, the best known algorithm is still Luby's algorithm that takes log-n rounds. And after a lot of work, in fact, a lot of exciting work in the last few years, I mean, we have a new result that solves MIS in O of log delta plus polylog log-n rounds. This is essentially the best possible in terms of delta, the maximum degree. But having said that, still the best known running time is still log-n, even for randomized algorithms. And these are randomized algorithms. So what is the situation from the lower bound side? We have the famous lower bound by Kun et al. That gives log delta that shows that MIS cannot be solved better than log delta by log delta or square root log n by log n rounds. And this means that if delta is little omega of 2 to the square root log n, one cannot hope for algorithms that are faster than square root log n by log n rounds. And so this sort of an absolute lower bound for MIS algorithms as far as time complexity is concerned. And recently there is a result by Baliu et al. That shows that one cannot even hope for little of delta round algorithms when delta is somewhat small. For example, then delta is somewhat smaller than log n for randomized algorithms, and delta is smaller than log n for deterministic algorithms. So that's the situation with respect to MIS today. And the point is essentially all MIS algorithms till now have focused on measuring the worst case number of rounds for nodes to finish. So in this paper, we take an alternate approach that focuses on designing algorithms. MIS algorithms are more generally distributed algorithms that are motivated by energy considerations. Okay. So, for example, in ad hoc wireless and sensor networks where MIS can be an important subroutine, a major concern is saving the total amount of energy spent by nodes or equivalently the average energy spent by a node during the course of an algorithm. So in such networks, significant energy is spent by a node even when it is just idle, that is just listening, waiting to hear from or listen to its neighbor. Okay, so the energy consumption of a node in the sleeping state, that is when it has switched off its communication devices, that it's not sending, receiving, or receiving, then that sleeping state, the energy consumption is significantly less than even when it is idle. Okay, so a node may judiciously enter and exit sleeping states to save energy during the course of an algorithm, and this is actually exploited in practice in actually in real protocols for sensor networks and all. The MAC layer, for example, provides support for switching between sleeping and awake states. Okay, so the sleeping model that we are positing in this paper captures this phenomena by imposing actually no cost for when a node is sleeping, and only when the node is awake we count the number of rounds, or we count the cost of the algorithm. Okay, so in a nutshell, what is the sleeping model? It's basically the same as the traditional distributed computing model. So you can apply it to the traditional congest model or local model with the following modification. So in the traditional model, a node is always awake. Here in the sleeping model, a node can be in 2 states, asleep or awake. And at the start of the execution, every node is awake, and a node can decide to sleep starting at any round of its choice, and thus moving from awake to sleep state, and it can wake up at any specified round in a later state. So we assume that all nodes know the correct round number whenever they're awake. And this is, I told you, as mentioned earlier, in practice, there is a way to implement this, for example, using MAC layers. So you can set up an alarm or interrupt when you go to sleep to wake up at a specified round or a specified time later. So the main thing is when the node is asleep, it does not send or receive messages, nor it does perform any local computation. Okay, so it's basically, you can consider the node to be dead. And more importantly, the messages sent to the node by other nodes during this, when it is sleeping, is also lost. So there's no buffering or anything. So when it's sleeping, the node is completely dead. So you cannot communicate or do anything with the node. So then that's the reason why we don't count sleeping nodes for any time, local, or message complexity. Okay, so what is the measure that we use? So in the sleeping model, there are two key measures. One is the node averaged awake complexity, okay, which is for deterministic algorithms, you can define it like this. So for a node, we let AV be the number of awake rounds needed for V to finish. Okay, so from the start till the node terminates, finishes its computation. So let AV be the number of such rounds. And the node averaged awake complexity is simply the average of these AVs. Okay, so the average number of awake rounds of a node. And for randomized algorithms, this will be a random variable. So AV be the random variable denoting the number of awake rounds needed for V to finish. And we can define a random variable that is the average of these random variables. And the expected node averaged awake complexity of the randomized algorithm is simply the expectation of this random variable. So in this paper, we mainly focus on the expected node averaged awake complexity of a randomized algorithm. However, one can study other properties like high probability bounds on A and so on. And besides this, we can also have a worst case awake complexity measure. This is the worst case number of awake rounds from the start and taken by a node to finish the algorithm. And that is simply, if AV is the number of awake rounds, its worst case awake complexity is simply the max AV over all V. And of course, we have the traditional worst case complexity, which has been used basically till now, is simply the worst case number of rounds taken by a node to finish. This includes both awake and sleeping rounds. So the central question that we want to design in this paper is that we want to address in this paper is that, can we design a distributed MIS algorithm with constant rounds node averaged awake complexity? Okay, so there are two main motivations, as I said before. One is to design energy efficient algorithms, because this captures the average is also equivalent to looking at the total time, total number of rounds and node is awake. The second motivation is that if you really focus on the worst case number of rounds, as what traditional complexity measures do, we are sort of stuck with square root log n by log n rounds. Okay, so or even log delta rounds for reasonable delta. So the question is, if you are looking at average case complexity or node average complexity, can you do better? So can you even do constant rounds? So our main contribution is that we present an algorithm called sleeping MIS algorithm, and actually a modification of that called fast sleeping MIS that has constant node average awake complexity and log n worst case awake complexity. And in terms of the worst case complexity, the sleeping MIS algorithm takes polynomial rounds, but the fast sleeping algorithm is a simple modification of that, which improves it to polylog n rounds, in particular log to 3.4 n rounds. Okay, so that's the main result of this paper. So what is the main challenge in showing constant rounds node average complexity? So if you can show that a constant fraction of nodes finish in each round, then this will imply constant rounds node average complexity. Okay, so this is the point, is we don't know how to do this for an MIS algorithm. We don't know how to design algorithms such that in every round a constant number of nodes finish. If you can do that, we'll get a constant rounds node average complexity, even in the traditional model. Okay, so in the sleeping model, an additional difficulty is that since when a node is sleeping, you cannot, as any messages sent to it, you cannot communicate with it. Any messages sent to that node which is sleeping, those messages are lost. So you have to also worry about scheduling correctly the messages. So our sleeping MIS algorithm addresses all these and gets the constant node average complexity in the sleeping model. And it's a very simple algorithm. So it's a very simple randomized recursive algorithm. So totally divide and conquer type recursive algorithm. So what is the algorithm? So every node flips a fair coin. If the coin comes up X, the node falls asleep. Otherwise, it stays awake. And let's call S the set of sleeping nodes and A the set of awake nodes. And what we do is we recursively solve the problem by recursively invoking the algorithm on the subgraph of the awake nodes, okay, to compute the MIS of that subgraph, okay, and let the neighbors of the MIS be denoted as n of MA. Okay, these are the neighbors of the MIS in the subgraph A. So this is the picture. So we have a set of awake nodes, A is a set of awake nodes, S is a set of sleeping nodes, and MA is a set of the independent set computed on A, and B is the set of the subset of sleeping nodes excluding the neighbors of MA. So because the neighbors of MA cannot be in the independent set, so we have B, and now we recursively again compute the MIS on B. Okay, and the overall MIS is simply the union of MA and MB. Okay, so that's in a nutshell is the algorithm. So again, so S is a set of sleeping nodes, A is a set of awake nodes. We recursively we compute the MIS on A by recursively invoking the algorithm on A to compute the MIS of A. And the recursion bottoms out when the procedure is invoked on an empty graph. Okay, that's a sleeping MIS algorithm. It's very simple. We keep on tossing coins till we get a empty subgraph or a single node subgraph. Okay, in the single node, the node just joins the MIS, and we can easily show that if the recursion depth is say 3 log n, then this guarantees that the recursion will bottom out with high probability, and this shows that the MIS that we get is a correct MIS. So this itself is an MIS algorithm. It produces an MIS. Okay, now the main thing is once MA is determined, the nodes in S at the very top level, let's look at the top level. So the nodes in the sleeping state, they wake up at the appropriate time, basically the time taken for the recursive call to get over on the awake nodes. Then they synchronize, and every node in MA informs its neighbors that it's in the MIS. Okay, and the status of nodes in the MA and the neighbors, okay, including the nodes in S, they are fixed, and hence they terminate. Okay, so let S be the set, let B be the set of remaining set of sleeping nodes. Okay, they are of course awake at this point of synchronization, so they will then again be recursively compute the MIS on the set of B. Okay, but again recursively invoking that. This is what that figure showed. Okay, and of course the overall MIS is there. So what is the main idea behind this analysis? So basically it seems that we have done nothing. I mean, it's a very simple algorithm where you simply keep off the nodes awake and off the nodes sleeping, and it seems that we have not done anything. But the key thing is that when the recursion returns from the set of awake nodes, the MIS computed on A, M of A, it dominates A and of course kills A, right? So all those nodes are finished. But the main thing about sleeping is that MA also dominates some of the nodes in S. Okay, so it eliminates all the neighbors of MA in S, and also eliminates any remaining isolated nodes in S. So after neighbors of MA in S are isolated, some nodes might be isolated in S. So of course they all join the MIS, they're also isolated. Okay, and the key technical contribution, one of the main technical lemma in the paper is what we call as the pruning lemma, which shows that on average, at least 1/4 fraction of the nodes in S will be eliminated when the recursive call finishes on. Okay, so the main challenge in proving the pruning lemma is that A is fixed by sampling, because we're sampling random nodes, and the MIS of A does not depend on S, because we don't know what the MIS is computed on A without knowledge of S. Okay, but still we need to show a constant fraction of nodes in S are eliminated. Of course, if in principle, you can use any MIS algorithm on A to compute the MIS of A. But it's presumable that there might be some MIS algorithms which may not eliminate many nodes in S. Okay, so it might be very small or whatever. So it may not, of course, it will eliminate nodes in A, but it will not eliminate nodes in S. Okay. So on the other hand, what one can show fairly easily that this is a nice exercise. Suppose we fix first an MIS of G and then randomly sample a subset A. Okay, we compute MIS of G by using some algorithm, let's say Luby's algorithm, and then randomly sample a subset A. Okay, and then we can argue on expectation that half of the nodes in S, okay, will either be dominated by MA, will be neighbors of MA, or be isolated after removal of neighbors of MA. Okay, so this is easy to do, but the point is this is not helpful for computing the MIS, because the whole point is in computing the MIS, so we don't want to compute an MIS first and then do the sampling. We sample first and then compute an MIS. So there is this dependence. So the dependence is handled by our algorithm in the most straightforward way. We use the sampling itself. Since we are using sampling itself to find an MIS, we have to use the principle of deferred deletions to analyze this process and show that even despite sampling first and then finding the MIS, this will still eliminate a constant fraction of nodes in the sleeping set. Okay. So this is the main lemma. I mean, I don't have time to show this, but the proof is in the paper. I encourage you to look in the paper for the proof. So the upshot is that the pruning lemma guarantees that a quarter of a fraction of the nodes in the graph terminate without being included in either of the two recursive calls. Okay, so the status of these nodes which are eliminated they are awake for only a constant number of nodes. Okay, in the first round, in the beginning, and when they are synchronized. So now using this, it's quite easy to show a constant rounds node average complexity because the two recursive calls operate only on at most 3/4 fraction of the given nodes on expectation. So recursively this propagates down the recursive tree and recursion tree, and then so what it means at level I, the number of nodes that are in play at that level is at most 3/4 to the I times n. This is the expected number of nodes, and of course in every the number of rounds per node outside the recursive calls is constant, right? So number of awake rounds. So the expected overall node averaged awake complexity is 1 by n, just sum up all the things. Sigma I is equal to 1 to infinity, 3/4 to the I n is constant. Okay, so that's how you get the node average complexity. So the worst case complexity, you can see that each node is awake for a constant number of rounds at every level of the recursion. So the recursion depth is 3 log n. So the worst case awake complexity is simply O of log n rounds. And if you want to look at the traditional worst case complexity, that's n cubed, because that's basically as much as the number of nodes in the tree, which is O of n cubed. So basically, if you look at the node that is at the lowest depth on the right, that will finish last, and that might take O of n cubed time. Okay. So our main thing, so the main point of the rest of the talk is to show how you can improve the worst case complexity from polynomial to polylogarithmic. And that is the main result of the paper. I mean, this fast sleeping MIS, which is actually a simple modification of the sleeping MIS that gives you the same node averaged awake complexity constant and log n worst case awake complexity, but as log to the 3.4n node averaged complexity, that means in the traditional model, which includes also sleeping grounds, and of course also log to the 3.4n and worst case complexity in the traditional model. Okay, so how do you do this? So the modification is just one simple modification, is that we truncate the recursion tree of the sleeping MIS to depth L log n. Okay, for a suitable constant n L, so we have to choose the fixed particular constant to get the best possible bound. Instead of allowing the recursion to go up to 3 log n, we truncate it at L log n, and when you truncate it at that level, we use a different algorithm which is called GREEDYMIS to solve the MIS at that level. So the GREEDYMIS is actually a well-known algorithm. So what is this GREEDYMIS algorithm? It is a MIS algorithm which operates as follows. So you first order the nodes or the vertices according to some random ordering, okay? And in each round, all vertices with the highest rank among the neighbors are added to the independent set, and they are removed from the graph along with the neighbors. And the process continues iteratively until the resulting graph is empty. So you can even think of this as a sequential process, but of course you can do it distributedly by doing all nodes that can get into the independent set in any round, they get into the set simultaneously. Okay, so the important thing to note is that just like our algorithm, in this GREEDYMIS also, the random ranking is chosen only once. Okay, so the random permutation of the vertices is done only once. And there's a nice result by Fisher and Newer in SORA 2018, which shows that this GREEDYMIS algorithm also runs in log n rounds with high probability, like the Luby's algorithm. Okay, so the GREEDYMIS, and the nice property of GREEDYMIS is that it always produces what is known as a lexicographically fast MIS. That means it always produces the same result once an ordering of the vertices is fixed. It means the MIS is fixed once the ordering is fixed. So you can note that sleeping MIS is exactly the same thing. It also produces the lexicographically fast MIS as well. So basically, the two algorithms are essentially one and the same. Okay, so at any given level I, the recursion tree would be identical if GREEDYMIS is used to solve at that level. Okay, so GREEDYMIS can replace sleeping MIS. So basically, you can replace the subtree computation at that level. Okay, so that's what this shows. So we have this recursion tree. So instead of going to 3 log n, we truncate at L log n, and at this level, we just use the GREEDYMIS to solve the MIS at that level. Okay, so we set the depth of recursion to be L log n, and if you do the math, then this is the L that is the best, log of 1 by log of 4 by 3 to the base 2. That's the best L. Okay, and the analysis is exactly same as the sleeping MIS algorithm in all levels except the base case. Okay, so the pruning lemma guarantees that the total expected number of nodes participating at depth L log n is this 3 by 4, because it reduces 3 by 4 to the power I at each level. So at this depth, it is going to be 3 by 4 L log n times n, and by this choice of L, we have half to the log n times n. This is n by log n. Okay, and this explains why we chose the depth to be L log n, because we get n by n. We want the number of nodes to be n by log n. Okay, so the greedy algorithm takes with high probability only log n rounds to solve MIS. Okay, in particular at this base case as well. So, and each node participating at this level stays awake for a long time. That means at least for log n time. Okay, so in the worst case. So but since there are only few nodes at this level, there are only n by log n nodes at this level, the total number of, the total awake time for all these participating nodes is n by log n times O of log n equals O of n. Okay, and that's the reason why I need to get this n by log n to cancel this log n. So that's why I went to that depth. Okay, and of course, the total is O of n. So dividing by n, we get the awake complexity per node at the base level to be O of n. Okay, so the overall node average complexity is simply the node average complexity of the recursion calls plus the node average complexity of the base cases. The node average complexity of recursion calls is just like before. I mean, you get only constant. We get a constant overall, and at the base we get constant base case. So the overall is constant. Okay, and how do you get the worst case complexity? The worst case complexity is simply, you have to look at the entire recursion tree. So the number of leaves at the recursion tree is simply the recursion tree nodes at depth L. It's depth L log n, which is 2 to the L log n, which is log n to the L. And the total time taken for executing one branch of the recursion tree from root to leaf is the time taken to traverse from root to leaf plus time taken to solve the base case of the leaf, right? So this is the depth of the recursion tree times constant, because at each node each node spends only constant number of rounds, plus log n to solve the base case, right? Because the GREEDYMIS takes log n rounds. So the depth is log n plus log n, so you get log n worst case. So same worst case time as before. And the total time is for executing the entire recursion tree is the time taken for executing one branch of the recursion tree times the number of leaves of the recursion tree. So one branch takes log n time from the previous from this, and the number of leaves is simply log n to the L from here. So overall we have log L to log to the L plus 1 n. Okay, that is log to 3.4 n for this particular L. Okay, so that's basically shows that the worst case complexity is log to 3.4 n. It's POI-log. Okay, so that essentially concludes the technical part of the talk. Okay, and to summarize our work, I mean, the key takeaways from this work are as follows. So we posit the sleeping model, which is we believe is a more faithful model for real world networks, especially networks that are energy constrained, and this can be useful for designing energy efficient distributed algorithms. And the sleeping model actually naturally leads to this two complexity measures: node averaged away complexity, and even node worst case away complexity. Okay, and we design and analyze a distributed randomized MIS algorithm that succeeds with high probability and has constant node averaged away complexity. And we further show how to improve the worst case, that is the traditional worst case complexity, to POI-log n, while still keeping the node averaged complexity to be constant. Okay, so there are many important open questions that can be, I mean, that arises from this work. Is one is, can we get a distributed MIS algorithm with constant node averaged away complexity and log n worst case complexity? Because log n worst case complexity is the best possible that we know till now. So can we get log n instead of some POI-log n? And recently we are aware of a work by Mohsen Ghaffari that answers this question. So he gives an algorithm that has constant node average away complexity and log n worst case complexity. And the second, I would say important open problem is, can we get a distributed MIS with constant or even little of log n node average complexity in the traditional one? So nobody knows whether such an algorithm exists till now. And the third, which is also very interesting, I would say, is like, can we design better distributed algorithms for other important graph problems in the sleeping mode? And this might be more realistic for the real world purposes. Thank you.